Hi, everybody. Welcome back to part two of the podcast episode on crash absorption with Carlos Moreno from Warwick University. The first episode was really interesting, and I am sure that this will beat it, because here we'll go deeper into some applications, and we'll also look at some video that Carlos has made showing how a crash absorber can work. So take a look at this. You will really enjoy it. Thank you.
Yeah, and then we try to combine this TWIP material with a new design method where we make metal powder extrusion to make very complex shaped geometries. And I know you made some trials on it, and I would love if you could share how it looked.
Yeah, absolutely. Yeah. Another thing that we might want to consider is like, so for instance, this project was done in the background of railway energy absorbers. In railway energy absorbers, all these absorbers are not only required to absorb energy, but they also need to prevent any anti-climbing between two vehicles. What that means is basically that the vehicle at the front, usually when it's crashing and is pitching, so the nose is going down, whereas the back obviously is tilting back upwards, whereas the following vehicle is doing exactly the same. It's pitching, and at that particular moment, you would have a misalignment between those energy absorbers. If that misalignment is severe enough, one of the vehicles can be overridden by the other, which is the worst situation that could happen in a train crash scenario, whereas one deck of the train swipes the other deck. That's a catastrophe. You don't want that to happen. So
you would cut everything above 20 centimeters in height.
So that needs to be prevented at all cost. So basically, these elements not only require to absorb the energy, but they have to resist that bending that or relative bending that happens in between them. So we are not looking just for a material that absorbs them, or the best material to absorb energy, but you could also try to minimize or optimize that design so that bending, which is going to happen in this particular plane, does not occur. So the tube or whichever element you have there is going to be collapsing actually, whereas at the same time preventing the buckling in that direction. And that's what caught our eye at the time from the columns that you provided, because you can basically design the section or a steel section to whichever shape you want, which is not usually the case. Steel extrusions is like very difficult to make. In this case, you can design. You have like total freedom to design a section, but at the same time, you get the benefits of steel, and not just steel, but the steel that you just described, like with strength and ductility at the same time. Yes.
Yeah. Do you have a video of it you'd share to give some insight in how it works?
So if I can show a test that was done on one of these columns, perhaps I should let me show this first, and you can see how this is the section of the column that I was referring to. So this is the section as you designed it at the time, or as it came to us, and you can see it's a quite intricate section, and that suggests that you probably can design anything you want, basically. And as an example, you could crash this laterally and see what kind of response you get out of that. We did a simulation of this. You can see if this is a platen crashing laterally these columns, and you can get a response from that you can see on the right hand side, and you can see that this pretty much corresponds to the ideal scenario of force stroke, where you have a very constant force over a large displacement. So, but the challenge here would be to do this in a longitudinal alignment or direction, because that would push this force
a lot higher,
a lot higher than this. So you would get a much larger force over the same displacement. So when you integrate that area, as you said before, you would get a massive amount of energy dissipated. So that's where this video or this test is doing. So you turn the column on its feet, and you crash it actually, and you can see how it behaves. And you can see all those lobes, all that pattern that is alongside as this column is being compressed. And this is quite interesting, because those lobes that we could see, for instance, here. Let's see if I can rewind this. You see all those lobes. That's the length of the progressive buckling. So the shorter that length, the more constant the force is going to be, because this is going to be a progressive buckling element, as I described it previously, where you would have peaks and troughs. But because that distance between lobes there, between that pattern, is quite small, the force is, even though it's going to still vary from a maximum to a minimum, that's going to reduce that peak force range, which is precisely what you want.
So what is how do you measure the energy absorption? Do you have a number per volume or a number per kg of the material, or how do you evaluate crashworthiness?
Usually a measurement that is widely accepted in industry is the SEA, the specific energy absorption. So that is usually to compare different energy absorber methodologies. That what it is like you take your whole element or your device, and you have a mass, whatever mass that device happens to have, and then when you crash it, you measure the energy absorption. So the energy, and you just divide it, is the ratio of the energy to the mass of the device. So you can think, for instance, to that concentric tubes I shown before. They have a very good energy absorption, but then the mass is large.
It was massive, and you only use a certain amount of the material.
Yes. Another measurement that you have is the force efficiency or the stroke efficiency. The force efficiency in particular is what is measuring what is the ratio between the peak force to the mean force. So in those cases, those tubes would get a good mark or a good score, because the force is quite constant. So you would get a quite high force efficiency. But then when you go to the specific energy absorption, that reduces significantly. I think from literature, the amount, the specific energy absorption for these tubes, which are typically called deformation tubes, is about 10 kilojoules per kilogram. That's the value that you aim for, or the mean value. When you go to crash cans, like the ones that they use in automotive, because you don't have a mandrel, they're lighter. When it comes to a specific energy absorption, the score is higher, So you get better values. It could be depending on how much it compresses. You could be in the 20s or thereabouts. So, like for instance, what I'm showing on the picture here is the specific energy absorption of this column which I've seen being collapsed, and you can see that the values are quite high. You see values on the 50 or 60 kilojoules per kilogram. So that's what we were discussing before, that when you have a material which is strong and ductile at the same time, you probably can get this kind of response, which is a good score.
So what do you see for the future of crash absorption? Where will it go?
It's difficult to tell, because there's many different ways to absorb energy. We've seen some of them here, like those deforming tubes. There's other mechanisms like I could show another mechanism. Because if there's many different mechanisms, it's quite different to compare each other, because they all have different properties, as we've seen. So if you have a section that doesn't require any other mandrel to compress, then the specific energy absorption is very high. But then it might have a smaller force efficiency depending on how the peaks and troughs behave. So you might have a large peak compared to a lower mean, in which case the force efficiency reduces. So it's difficult to compare. So that's why when I mentioned before that some researchers are looking into those hybrid elements like deforming tubes or splitting tubes to incorporate into the automotive industry is in a different way to see it. So in the automotive, it seems that everyone uses crash cans, but these researchers, what they want to do is the opposite. They want to go from crash cans into different methodologies. In the railway, they are using the other hybrid energy absorbers like deforming tubes or splitting tubes. And perhaps the challenge would be like, can we incorporate things like these columns that work under progressive buckling into the railway industry and get similar performances? So obviously, it's not a mature technology in that sense. There's a lot of room for wiggling. So and that's why this project, like the one we have discussed with these columns, where you can change the section to pretty much do whatever you can dream of, is quite interesting. And you could and as we've seen the industry trying to incorporate those ones into the railway industry. So it's not a mature technology, so it's still lots of work to do and lots of room for improvement there.
But the driving force is, are we on level with the safety, or do we want higher level of safety, or is it just okay today and we just want to reduce price? What is the driving force today?
I would say that from the point of view of the commercial businesses, the industry, probably they follow the regulations. So basically, the regulation sets a number of scenarios, and they say you need to comply with this. What they do is try to comply with them with the regulation. If they have elements at the moment, the energy absorbers that does that, then the race is, as you said, is cost. So it seemed to me when I was there that the race was basically down to cost, but just because they're trying to follow the regulations. The regulations in railway, they are quite interesting because they only tell you that you need to prevent or you need to absorb the energy in case of crash scenarios up to 36 kilometers per hour, which is not a very large number. I think from studies where they claim that many of the collisions that happen in railway happen below 40 kilometers per hour. That's why they chose those numbers.
Yeah,
I think that is also driven by the fact that they assume that if there's crashes at higher speeds than 40 kilometers per hour, there's no easy solution at the moment. So basically they said, well, let's lower the requirements.
yeah.
So if you can start finding energy absorbers that they can absorb more in a controlled manner, then the regulators will jump into that. And they will say, well, if we can do this, then we are going to increase the speed of the speed requirement from 36 to 50 kilometers per hour. In which case the race would be on to develop these energy absorbers that are better performance than then. So we would shift the race from cost into performance, which would be which would be beneficial for for the users definitely.
Yeah,
but it would be a spur the industry. Yeah.
Yeah, Carlos, I have a last question, and it's pretty technical. When you make a tensile test, your result will vary when you vary the speed of your pulling force, and so typically when I make tests in my lab in a tensile test, I go pretty slow, absolutely not at all near 40 kilometers per hour, and not 100 as you typically do in a car.
Yeah.
How strong an influence does speed have on the energy absorption level in these designs? And can you do this in the lab? Can you test it in the lab, or is it so different from lab to real life speed that it is almost difficult or very difficult to explain?
No, I think it's quite well defined in the sense that the rate sensitivity of the materials can be relatively easily tested. Mm-hmm. So you can have, as you said, you can use the universal tensile machines, but at speed. Here in Warwick University, we have the VHS that can test at rates up to 1,000. So you
1,000
could take 1,000 microstrain over microstrain. So it would be like I don't know how could you translate that in speed. Well, it would depend, but it's like typically in a car crash for 60 kilometers per hour, the crash cans undergo between 100 or 200 microstrain over microstrain. So it's unitless. Yeah, but it's around that 60 kilometers per hour in a crash can might translate into around 200, a value of 200 in train crashes because it's a slower speed, and then typically it's less. But then I remember from my PhD, when I was looking into these deforming tubes, you could have values from as well 100 to 200 when it's swelling, radial expansion. So you can do tensile test at that kind of speed and get the response of the material. Steels are, depending on the grade of steel, they are more or less responsive to or sensitive to rate. Like I think mild steels tend to be more sensitive to speed, whereas if you have like very high strength steels, they are less sensitive to rates. So that obviously needs to be taken into consideration if you are simulating that, because depending on the speed of the crash, you're gonna have different forces, which if the regulation says that is the acceleration, there's a maximum acceleration that can be transferred to the occupants, then you cannot have the steel giving you 3 times the force. So you need to consider that when you are designing the device.
Absolutely.
Yeah, there's other considerations like for the deforming steels, because you also have friction, and in that case, friction goes the opposite way. The higher the speed, the lower the friction. So in this case, you have the opposite effect. As the train crashes at a higher speed, you might be reducing the force, while you are deprotecting the vehicle. So you need to be quite careful of when you design these elements of how they're going to respond to that.
So when you are
sorry to interrupt. I just want to take a little deeper dive into this relation between speed and tensile properties, because it is very well known, especially for plastic, that if you deform with a higher speed or lower speed, the properties are varying a lot. But it also happens with metals. You can see that on the curve here. This is with 3 different speeds, and you can easily see that there is a variation on how it deforms. You can see that you can go with very different speeds on the machines today. So I would advise to take a little deeper look into how speed affects the mechanical properties, especially the elongation and the strength. But it's not very known that this factor is there. But one of my previous guests in the episode on electrocenter forging, Alessandro Fais, he is really using this, because he is deforming material with such a high speed that it doesn't really recognize that it has been deformed before it's over. So I would recommend to go to the episode on electrocenter forging to have a look at how that works, because that is incredible. He is able to deform and shape components in materials that under normal condition cannot be deformed. So enjoy looking at Alessandro if you take that step.
Are trying to develop a solution with a very high SEA, what's it called that? The crash absorption density. Then you are able to save the number of kilos you put on a car, or you could improve the crashworthiness if you keep the same amount of material. Where do you think we will go in the future? Will it be reducing the weight of the car, saving material to be more sustainable? I know the light weighting of cars can reduce carbon emissions. So what will be the driving force? Will it be sustainability, environmental protection, or will it be human safety?
I would imagine that at the moment it would be lightweighting, cost, and environmental considerations. So the heat seems to be on reducing weight. That's definitely in automotive. Is also coming to railway now. even though, as I said before, that weight is not as a stringent requirement as there's also that development, and you see other companies that have developed energy absorbers for railway, which are made of composites, so to reduce weight. I would say that at the moment, unless something changes, the race would be in lightweighting. But as we discussed, if they find that they could actually meet both requirements, regulators might increase the requirements, or then, and in which case it would be like you can use stronger materials to give you more strength over the stroke.
Yeah.
But yeah, I think that would entirely depend on regulators recognize or seeing the need for better human protection. Don't think that would be driven by businesses. I think businesses at the moment would be or are happier into the lightweighting race.
Yeah. Perfect. Thank you very much. Carlos, if people want to learn more about crashworthiness, where could they look? Are there conferences? Are there books you could recommend, or where can you learn more?
Yes, I guess regulations is a big part of the passive safety industry. So you could look into regulations, and then you can know then what people is trying to solve. So what are the regulations for automotive? What are the regulations for railway? I know that in aerospace there's no much of energy absorbers, but I remember from the time I work in aerospace and helicopters, you do have energy absorbers on the seat of the pilots. So the seat of the pilots is a column that splits. So when the helicopter fails, they can start falling, and the rotor goes into auto rotation because of the wind going through the blades. So they get some sort of floating or buoyancy. So they're not going to fall like a stone. And then when they fall, provided that they fall still on their feet, the seat is going to protect the lives of the pilots. So yeah, regulations determine this kind. So you can look into regulations. There's for railway, there's the biggest conference in passive safety is held every 2 years in Germany. It's typically in Berlin. It's called the passive safety in railway. So if you would like to Google that, you would find what's the latest advances from the main players in this kind of industry. I guess if you are more into academia, I remember from when I was doing my literature review, there's not so much in academia. But you do find some books that talk about energy absorbers, like the different energy absorbers that are there, like whether it's progressive buckling, radial expansion, splitting, or is composites being pulverized as you compress them. So if you want to, I could go back to my literature review and suggest some books or papers that would be like seminal to the.
That would be perfect. Then I can put them in the comments on the YouTube video, so people can look them up.
No worries.
Wonderful. Thank you very much, Carlos. I learned something new today.
No, and it's a pleasure talking to you, Peter, always.
Thank you very much.
Thank you, Peter.
See you.
See you later. Bye now.
Bye.
So, how did you like the episode on crash absorption? Do you feel safe now when going into a train or a car? I do. With people like Carlos who develop solutions like that, it is a lot safer than you really think. So I hope that you also feel safe when you go traveling now. If you like this episode, and if you want to learn more, please subscribe to the YouTube channel Everyday Metallurgy, and I will come back with a lot more information. And you can also look back in the old episodes. We have more than 40 episodes now on different subjects within metallurgy. So enjoy and spend hours on your learning. Thank you very much.